So in the last class, we were doing the derivation for stretching of a line element, and then also we figured out the longitudinal strain. And the formula that we derived was that lambda square, the stretching square, at a position capital X in the reference configuration, and for a line element directed along the direction M, that's equal to C M dot with M. Okay, where C is the right Cauchy green tensor. Okay, so let me again draw that reference and deformed configuration. So here is the point capital X and a infinitesimal line element, infinitesimal, directed along M. Okay, you remember that this direction here, this has to be the direction in the reference configuration. This is a direction in the reference configuration. It's not the direction here in the deformed configuration. Okay, you see a line element having direction M will have a different direction in the deformed configuration. So it's not the same direction. Let us now talk about the formula for change in angle between line elements. Okay, and this can be used to obtain shear strain, because shear strain is related to change in angle, right? And you see, this formula is general. Whatever is the kind of deformation, you can always apply this formula. Whether it is elastic, plastic, elastoplastic, you can always apply this formula. If you know the deformation map little f, find out the deformation gradient, and then use that formula. Okay, now for change in angle, suppose I am again at the point capital X and think of two infinitesimal line elements, delta capital X and delta capital Y. Okay, and after deformation, they will go somewhere else. Let us say to point small x, and it would become, let us say, delta small x and delta small y. And I want to know what is the change in angle. So suppose that the angle in the deformed configuration is theta. Okay, so what is that going to be? I mean, how do I get that angle in the deformed configuration? So we all know that the angle cos theta is same as delta little x dot delta little y over the magnitudes, right? Okay, now let us use the formula. We know how line element is transformed. So this is then big F delta capital X dot with big F delta capital Y, right? You see, very simple, because we know they transform through the deformation gradient. Okay, and then you have some higher order term here. Can you recognize what will that higher order term be? So maybe I should work it out in a little bit more detail, then you will be able to appreciate. So this term plus big O delta capital X square dot with, so this has to be dotted with big F delta capital Y plus big O delta capital Y square, okay, and then you have to divide by, so you see the final length would be lambda, the stretching, times the undeformed length, isn't it? And then you have some error term also, plus big O delta capital X whole square, right? So this is the first bracket, and then you have to look for similarly the second bracket, which is, and yeah, and by the way, this lambda is the lambda of X, no, it is of delta X, so I'll write it here, lambda delta X. And likewise you have lambda delta Y, okay, into delta Y. See, it is very important to understand the error terms, then only you can appreciate what is going on. Plus big O delta capital Y whole square. Can you see me? Can you see my screen?
Yes, sir.
Yes,
Okay,
sir.
thank you. All right, so what do I do next is, so I'm going to write this as, take this delta capital X on the numerator, take this on the numerator, likewise this delta Y, take it on the numerator, so it becomes F into M, isn't it? Delta capital X by mod of delta capital X is M plus big O delta capital X dot with F, and let us say this is N, okay, two directions M and N, plus big O delta capital Y, we can also keep this habit that everything in the reference configuration we denote by capital letters. So if we think of that, then the direction M and N, we can make it capital also. Okay, let's make it capital. So we can also go up and make it capital. So here we have M, so this is CM dot with M, and this is capital M, and this becomes small m. So capital M changes to small m. So in the deformed configuration, everything is small letter. Okay, so we come back here, and then we have to divide by lambda of delta capital X, and we know that. So we could also write it as lambda capital M into lambda capital N, and then you have the remaining term, which is 1 plus big O delta x. Please interrupt me if you're not able to follow, because in the examination when I ask you for derivation, you have to do everything methodically. You should not miss out a step, otherwise I'll cut your marks. Okay, now should we do, see, it's, we are doing everything exact. With the error term written, we are doing everything exactly. So now let us do the multiplication. So we have f m dot with f and now can you see what are the error terms? We have big O delta capital X plus big O delta capital Y, isn't it? So that's the numerator, and then the denominator will now go up, and keep this lambdas below, lambda m, lambda n, okay, and the remaining we bring it in the numerator with a power minus 1. So this is now 1 plus big O delta capital X to the power minus 1. So we have to go very, very slowly. No problem, you won't make any mistake. Okay, and this is delta capital Y to the power minus 1. So what should you do now? So you can now use binomial expansion. Okay, this is, by the way, this thing is whole to the power minus 1. Are you guys with me? Okay, now what do you think? What can we do? You see, each of these terms, when you do binomial expansion, this simply becomes 1 minus big O delta capital X. Are you guys aware of binomial expansion? If you are not able to follow, please let me know. Are you following, Roshan? Is he there, Roshan?
Sir, he is absent.
He's absent? Okay. Um, Anybody else? Devjit? Are you able to follow till now?
Yes, sir. Sir, I just one step that how are you breaking up the dot product into just three terms that I couldn't get?
Yeah, I mean, there is a fourth term also, big O delta capital X into delta capital Y, right?
Yes, sir.
So that is in one of these two. Like I was
Okay.
telling you, no?
Yes,
Yes,
that we can add in O function, big O
exactly.
function.
Yes, in any of them.
Okay, sir.
So, and this binomial thing, are you guys able to follow this binomial thing?
Yes,
You
sir.
know, I have this formula 1 plus x to the power minus 1.
Yes, sir.
That
This
is 1 minus x plus x square by 2 factorial minus x cube by 3 factorial. Now, if x is very small, then it is 1 minus big O x, isn't it? 1 minus big O x, because everything goes in that big O. And on the numerator, the left hand side, 1 plus big O x. So to the power minus 1 becomes 1 minus big O x. Okay. Now you multiply everything, you see that this is simply Fm dot with Fn plus the same thing that's written there, big O delta x plus big O delta y. So everything gets engulfed, the numerator, and then you have to divide by lambda m lambda n. So that division comes here, lambda m lambda n, and the rest remains as it is. And if you bring the f on the other side, so this is formula for cos theta, by the way. So cos theta finally is c m dot with n divided by lambda m into lambda n. So this is the formula for cos theta, and theta is the deformed angle. So what did we do here? We simply did the limit, no? So this was done by limit delta x going to 0 as well as delta y going to 0. And why are we taking this limit? Because we want to know the change in angle between line elements at big X itself. So therefore the line elements have to be taken very, very small. And so we take this limit. Okay? So you see, final formula is really, really nice. Now from here, with this formula, can we figure out the change in angle? You know, you have learned in your solid mechanics, strength of materials UG course, that shear strain gamma is 90 minus theta, isn't it? 90 minus the final angle. Can you guys recall? And actually it's in pi, so it has to be pi minus pi by 2, which is 90 degree minus theta. Okay? And if you recall its formula, what was it? Gamma 1, 2, for example, was del u1 by del x2 plus del u2 by del x1. Isn't it? So can we extract that formula from this non-linear thing? So this formula on the right hand side, so this holds only for linear elasticity. And here I am saying that big M, the first line element is E1, and big N, the second line element is E2. And from your strength of materials course, the line elements were perpendicular. So shear strain was defined to be the change in angle between perpendicular line elements. Okay, so you take M equal to E1, N equal to E2, they are perpendicular, and the formula for shear strain was this. But this was in linear elasticity course, where the deformation is assumed to be very, very small. That is, we assume that ui over j, this magnitude is much, much less. General formula. You see on the left hand side, this is general form, general for large deformation. So you'll have to derive this as part of assignment 1. There will be something more. Part of assignment 1. And you have to submit in a week. Okay. So this is the formula for change in angle. What are the other things? So we found out the change in length, change in angle. Then the next thing would be, for example, change in volume. Or let us say relating deformed and undeformed volume.
So we will have to relate this general formula to the particular linear elasticity case for the part of assignment 1.
Yes. Okay.
Okay.
All right. So how do we relate volumes? So you have to take volume elements now. So again, you have reference and deformed configuration. And you are at a point capital X, which is going to point capital Y. So, for volume element, you have to take three line elements as the sides of the parallelogram. And from there, you can form your parallelopiped, sorry, the sides of the parallelopiped. So, let me show you how we can do it. So, this is one line element, this is another one, and then this is the third one. Okay, so this is the parallel pipe. So this one is delta capital X. This one is delta capital Y. Okay. And this thing here is the capital Z. So this volume element will also change to something else over here. So it will still remain a parallel pipe, but the angles between the sides will change. Okay, suppose it becomes this. So this is delta small x. Sorry, this is small x, no? Small x. And this one is delta small x. This one is delta small y. And delta small z is delta small z. So what is the, let us suppose I denote the volume by say big V. The undeformed volume is big V and deformed volume is small v. So what is the volume of a parallel pipe? If you know the three sides, then the volume is simply the scalar triple product. Okay, that's scalar triple product, delta x dot delta y cross product delta z. And therefore the volume in the deformed configuration, the same volume is delta small x dot product delta small y cross product delta small z. Okay. Now how can we relate these two? Because our goal would be to get volumetric strain. So volumetric strain, if I denote by epsilon v, epsilon with a v, then that's simply small v by big V minus 1, and then you take the limit big V going to 0. Okay. And how can you let big V go to 0? take all the three, delta capital X, delta capital Y, delta capital Z, all the three lengths go to 0, it will automatically shrink to a point. Okay, and then only strain or volumetric strain at the point itself. Okay, please stop me if you're not able to follow. So let us first find out what is small v by capital V. Now for small v formula, we are going to use the deformation gradient thing. So it becomes big F delta capital X dot with F delta capital Y cross product big F delta capital Z. Okay, and what do you think, what will be the error term? Can you guys think of what would the error be? Anyone? Niranjana, what do you think? What will be the error term here?
Sir, big O mod of x square, mod of y square, mod of z square, delta z square.
Okay. Others, what do you think? Is that correct? See, what you have to do is, as earlier, for delta small x, you will write big F delta capital X plus big O delta capital X magnitude square. Likewise for this term and this term. And then you multiply them together. And you will see that it will be big O delta capital X whole square into delta capital Y into delta capital Z. That's what it will be. That's one of them. Then the second one will be big O delta capital X whole square into delta capital Y square. Okay, so first one is no square into delta capital Z. And then another one big O, that's delta capital X into delta capital Y into delta capital Z whole square. So that will be the error term here. And then you have to divide by delta capital X dot with delta capital Y cross product delta capital Z. Okay? And once you divide, what do you get? So what we will have is big F delta capital X dot with big F delta capital Y cross product big F delta capital Z divided by delta capital X dot with delta capital Y cross product delta capital Z plus the error term. Can you guess what will be the error term here? Tell me, when you divide, what happens to the error term? So what you are dividing by is of the order of delta X into delta Y into delta Z. So what happens to the error term finally?
Sir, big O of x plus big O of y, delta y plus big O of delta z, something like that.
Is that Devjit?
Yes, sir.
Okay, very good. So this becomes big O delta capital X plus big O delta capital Y plus big O delta capital Z. Okay. And further have a look at this term here. What is this thing? So for that you have to know a correspondence that a scalar triple product can also be realized as a determinant of a matrix. Are you guys aware of this? A scalar triple product can also be realized as the determinant of a matrix formed by the three vectors, or I should say a matrix whose columns are formed by the three vectors. With me what I'm saying here? So basically if you have A dot B cross C, then think of a matrix whose first column is A, second column is B, and third column is C. Okay, represent that in a coordinate system, it becomes a column. And take the determinant. So these two will be same. Can you prove it using indicial notation? What do you think? Can you prove it? So do you remember the formula for determinant? What formula for determinant? If your matrix is big A, or let's say big, I'll say some other matrix. Suppose it's a matrix big M, whose components are Mij. Then determinant of big M, if you recall from the first class, it's epsilon ijk M1, or let's say Mi1 Mj2 Mk3. Okay, can you recall this formula? That's for the determinant. You can brush up also. Now on the left hand side, I have this formula. Now think of what will be Mij here. What is Mij? So Mi1 is simply Ai. Mi2 is Bi. And Mi3 is Ci. Isn't it, for the matrix above? So you can come back here and write it as epsilon ijk ai bj ck. Okay, so this is the determinant of this matrix. But have a look at the left hand side. First of all, what is B cross C? B cross C. So B cross C, you can use the permutation symbol epsilon ijk bj ck ei. Right? That's B cross C. And I have to dot it with, so what will be A dot B cross C, which is same as epsilon ijk bj ck EI dot with A and make it A, let's say RER. And when you dot it becomes delta IR, so R becomes I. So you get the epsilon IJK AI BJ CK. And you can see this is what you have there. Okay, so we have proved this thing that a scalar triple product can also be realized as the determinant of a matrix with its columns formed by the three vectors. Okay, so with this definition in hand, big V then simply becomes determinant of the matrix whose columns are formed by delta capital X, delta capital Y, and delta capital Z. Isn't it? Are you guys with me? Anybody not able to follow? Adil?
Yes, sir.
Adil,
Yes, sir. Sir.
are you able to
Sir.
follow?
Yes, sir. Sir, I'm following you.
Anybody not following Niranjana? Is he absent? Niranjana?
Hello, sir. Yes, I'm able to follow, sir. Just a small bit of lag here.
Okay, everybody following then.
Yes, sir. I'm able to follow.
All right, now you see for small v, it then becomes determinant of delta little x, delta little y, delta little z. But then we know delta little x, delta little y, delta little z. I mean, see what it is here. I want f delta capital X. So I should write this as determinant of f into delta capital X. Then f into delta capital Y and f into delta capital Z. Okay, that was in the numerator, right? So this is denominator and that's numerator. Okay, now what do you think? This column here, f into delta capital X, is formed by the product of second order tensor big F with first order tensor delta big X. In the matrix form, it will simply be product of matrix of F multiplied with the column of delta X, isn't it? So this is same as determinant of big F into delta big X, then big F into delta big Y, and then big F into delta big Z. Are you guys following it? Please, if you have even slight problem, do ask me. And this can also be written as determinant of big F into delta capital X, delta capital Y, delta capital Z. Okay, which is same as, now you have product of two matrices and you have to take determinant, so it is same as determinant, it is same as product of the determinant of the two matrices, so it becomes determinant of big F into determinant of the other matrix. Okay, and finally, it is then determinant of the tensor big F multiplied with that volume big V. That's the definition of volume big V, no? Okay, did you guys understand this? I will be really surprised if you followed it.
Sir, we are breaking down that deformation gradient into matrix multiplication formula. That is the only thing that we are doing right here.
Yeah. Nomen Tomar, are you following?
Yes, sir.
I'm very surprised that you could follow it. Huh? How
I'm
do you
following you.
come from here to here? Can you explain to me? See, basically, this matrix here has been written as the product of two matrices. Can I do it? How did I do it?
Sir, product of 2 or product of 3, sir?
Product of two matrices. This is one matrix and this whole thing is another matrix. देखो सबसे पहले तुम्हें यही पता लग रहा है कि तुम्हें लगा कि प्रोडक्ट 3 है जबकि यहाँ प्रोडक्ट ऑफ टू मैट्रिसेस है तभी तो इसके नीचे जाके दो मैट्रिक्स का डिटरमिनेंट ले रहे हैं तीन मैट्रिक्स कहाँ है इसके नीचे I mean, you can prove it by showing that LHS is same as RHS also. That's another way to do it. So basically, think of a matrix which is formed by the following thing. And call this M. Okay, this is matrix M. Then what do you think is MI1? MI1 is what? The first column, right? This is MI1. Isn't that AIK into AK? Is that correct? AIK into AK? What is MI2? That's AIK into BK. Is that correct? And then what is MI3? That's AIK into CK. Isn't it? Because each of the columns are the product matrix and vector. And I said that this is same as writing it as matrix A multiplied with ABC. So let's call this thing as matrix, suppose B. So M, matrix M here is then big A into big B, right? Then what is MI1? What will be MI1? So M is product of two matrices. So MI1 is simply AIK into BK1. Am I right? AIK into BK1. But what is BK1? Look here, what is BK1? The first column. That's simply AK. Right? And this is what you also have here. as you can see this formula. So likewise, you can prove that Mi2 will be equal to Aik into Bk, and Mi3 is Aik into Ck. So that's the proof.
Okay, sir. Now I get it.
The other way is to, not really do it, but if you are comfortable with matrix vector multiplication, then you have to set when you multiply two matrices A and B, like here, the first column is formed by the matrix into the first column of second matrix. Second column will be matrix into the second column of second matrix. Third column will be the matrix into third column of second matrix. Okay, so I hope this is good for everyone. So finally, coming back to our original formula that is here, we have to come back here. So what is this then? This implies a small v by big V is equal to determinant of f into big V divided by big V plus these terms, right? But when you take the limit of big V going to 0, these error terms will go away, right? So here you have to take the limit big V going to 0. And this will imply epsilon V is then equal to determinant of f minus 1, isn't it? So this is a formula for volumetric strain for general large deformation. Okay, so I'll just write that down here again in a box. So epsilon V is determinant of f minus 1. So volumetric strain for large deformation. Now, do you remember from your strength of materials what was the formula for volumetric strain? Can you guys recall?
Sir, strain in x direction plus strain in y direction plus strain in z direction.
Okay, that's Saurabh Purani.
Yes, sir. Yes, sir.
Okay, that's true. But that formula holds only in linear elasticity when strain components are very, very small, or the displacement gradients are assumed to be very. But the formula that we have here right now, this holds for general displacement. The second assignment for assignment 1, second question. Show that epsilon V reduces to del U1 by del X1 plus del U2 by del X2 plus del U3 by del X3 if del Ui by del Xj is much less than 1. Okay, this is number problem 2, assignment 1. And you'll have to submit it in a week through Gradescope. And do it very nicely in the language that we are learning. Okay, so this is the formula for, so see, we found out longitudinal strain, we found out shear strain, we found out volumetric strain. From the formula of volumetric strain, you see it does not have any direction present here. There is no direction of line element present here. From the formula of angle change, it had the directions big M and big N. But here in the volumetric strain formula, the direction is not present. So what this tells us is that volumetric strain is unique at a point. There is only one volumetric strain at a point in the body. There are infinite longitudinal strains at a point in the body depending on which line element we are looking at. There are infinite combinations of shear strains at a point in the body depending on what pairs of line element we chose to find the angle change. But volumetric strain is unique at a point. Okay. So you see, we talked about line, we talked about angle, we talked about volume. Can you think of what is missing? What is it that we haven't discussed yet? That we are
area.
missing? Yeah, who is this guy?
So Devjit.
Devjit. Okay, very good. So how to relate area in undeformed and deformation? So how to relate area in undeformed and deformed configurations. So let us try to work this out. So for area, for an area element, we just need to take two line elements. So we are at a point capital X and think of line element delta capital X and delta capital Y. And the area vector is given by the cross product. So this area vector here, that's simply delta capital X cross product delta capital Y. That's the area vector. And when it deforms, goes to small x, and then it is this thing, delta small x, delta small y, and the area vector is then this parallelogram. Which is delta small x cross product delta small y. And we want to know how two area elements are related. Okay, and you see area is a vector. It has got a magnitude and also the direction. And the direction of the area is simply the normal to the area. So area is a vector whose direction is along the area normal. So SP, can you recall what is the formula for this area relation? Do you know? SP?
Sir, I could not recall this.
You can't recall? Okay. If I say this area, so it's a vector, no? So I will say it is the vector M into D capital S. Where M is the normal and D capital S is the magnitude. And here it is small m for the normal and D small s for the area. And I want to relate these. How is small m D small s related to big M D capital S? Okay, and big M D capital S, by the way, is same as delta capital X cross product delta capital Y. All right, so what do you guys think? how do I move? So it's the same old trick. So you have delta little x cross delta little y. So you can write it as big F delta capital X cross product big F delta capital Y plus the error term. And what is that error term going to be? Okay, can you guys recall the error term? So I'll just say it. This is big O delta capital X whole square into delta capital Y plus big O delta capital X into delta capital Y whole square. Okay. All right. Now what should we do? Any idea what can be done next? So basically focus on this thing over here. Sorry. This one. And let me dot it with delta. So we just found out that delta small x cross delta little y dot with delta little z, that's equal to big F into delta capital X cross product big F delta capital Y dot with big F delta capital Z. And of course then you have these errors also. Now concentrate on this term over here. So this is same as F delta capital X cross product delta capital Y. This F on the other side comes F transpose dot with delta capital Z. Can you write this? Isn't it? This is fine. But on the left hand side, we just learned this is also equal to determinant of F into capital X cross product delta capital Y dot with delta capital Z. Isn't it? Just learned this. So this is then also now bring this F transpose on the other side. How can I bring it on the side? You simply multiply with F inverse transpose. Okay, I can do it. I hope I'm not making any mistake. Let's see. Okay, no, because this is a scaling right now. So, okay, so right now we can't do it. Sorry. Now look at left hand side and right hand side. This holds, you see, this holds for arbitrary del z. This formula holds irrespective of what delta capital Z you choose. Okay? You know, so basically if you have a equation that A dot B is equal to C dot B for all B, if this holds for all B, then you can say that A is equal to C. Do you know this formula or this identity?
Yes, sir.
Yeah, so this is not difficult. You know, from here you can say, for example, A minus C dot B is equal to 0. Okay, and B is arbitrary. Means A minus C must be equal to 0 because B is arbitrary. If B were a constant, then this just says that A minus C is perpendicular to B. But because B is arbitrary, this means A minus C must be equal to 0 or A equal to C. Okay, so come back here. Because this holds for arbitrary delta z, this also implies that the determinant of big F into delta capital X cross product delta capital Y is equal to F transpose into F delta capital X cross product F delta capital Y. Okay, now you bring this on the other side by pre-multiplying this entire equation with F inverse transpose, and then what you have is F into F inverse transpose, okay, into this thing delta capital X cross product delta capital Y, and that's equal to F delta capital X cross product big F delta capital Y. Okay, and finally, you know, we are there. What is on the right hand side? You see, this is the deformed area, isn't it? This is delta little x cross product delta little y, isn't it? Of course, with an error term also, but that to 0 as you shrink the area. Okay, so I'll just say that this is equal to delta little x cross product delta little y error term. And finally, we can say that the deformed area is small m d small s is equal to undeformed, that is det f into F inverse transpose into big M into D capital S. Okay, so this I'll put in a very important formula. So you see, this is how you can relate deformed and undeformed area. Or you know, other way to write this is deformed area. Let us say I did not buy small for the area equal to det f F inverse transpose into big A. And you have to understand that the area has to be infinitesimally small. small a and big A are infinitesimally small. Okay, can we use this formula to find out how does the normal transform? How does the normal to the area transform? Okay, what do you think? So normal is, normal is the final deformed normal, and I want to know how is it related to big M. So what do you think? Related? You see this, you can use this formula. So small m is a unit vector, big M is also a unit vector because they are the normals. So this simply implies that small m is equal to det f. Well, we don't also need that. Simply F inverse transpose into big M divided by magnitude of F inverse transpose into big M. Okay, this is how the normals to area transform. Can you see this? See direction on both the sides. On the left hand side the direction is small m, on the right hand side you see here the left hand side the direction is small m, and right hand side the direction is F inverse transpose into big M. So that means small m has to be along F inverse transpose into big M because that's the only direction. But then we also know that small m is unit vector. So I simply divide by F inverse transpose m magnitude, and that's how you get the deformed normal. Okay, can you see that we had learned in the beginning that any line element, a line element transforms in the following way: delta little x is equal to big F into delta capital X. Transformation of line element. Okay, but then you contrast it with this normal. Normals are not transforming in this way. Can you think of what could be the reason? Why did it not happen that m is equal to, why it did not happen that this is equal to big F into big M divided by magnitude of big F into big M? Any idea why is this not correct? Anyone?
It's outward normal. It doesn't lie on the area.
Say again.
The small m is not lying on the area, like it is outward normal.
Small m. Well, small m is the normal, no? It's normal of the formed area.
Yes, sir. So it doesn't. It's outward normal, like it is not lying on that area. So the transformation of line element is not applicable.
So which transformation is not applicable? That delta little x equal to big F delta x? Is that what you're saying?
Ah, yes, sir. That transformation is not applicable to this. because it is not lying on.
Why it should not be applicable if it is not on the area, but it is some vector, then why it is not applicable? I think you are a bit close, but not correct really. Anybody else? Yeah? You have to think of it as, you see the area you're forming by delta capital X and delta capital Y, or delta small x and delta small y. So you have that tiny parallelogram. As you shrink the line elements, that parallelogram is also shrinking, but it is still an area. And the normal to that parallelogram is the small m. So during the shrinking process, always, small m is always the normal. Anyone else?
Sir, this may be because of the change in direction, like mm, the direct.
Yeah? Say again?
Yes, sir. Maybe change in direction or coordinate system.
What do you mean change direction? Change direction of what?
No, sir. The coordinate system or the reference frame may be changing.
So first of all, there is no coordinate system involved here. You see, the entire derivation is done using vectors. There is no coordinate system involved here.
Because, sir, if you look at the relationship, the magnitude is
Yeah.
changing.
Which magnitude?
The magnitude of unit vectors. M vector and the small m vector and capital M vector. Left hand side we have one magnitude is 1, whereas the right hand side the magnitude is F inverse transpose by F
Who said
inverse
no?
transpose.
That is not correct. On left hand side, the magnitude is d small s. You take the magnitude of the entire thing, you get d small s. So that's the area of the, that's the deformed area, magnitude of the deformed area. On the right hand side, when you take the magnitude, what you get is, it's not d capital S, it is the magnitude of the entire thing. D capital S multiplied by determinant of F into magnitude of F inverse transpose into M.
Comparing the unit vectors, normal vectors now. It is no more we are talking about the deformation of lines.
Yeah, it is not the
Now
deformation
we are
of
trying
line.
to
But you can see it precisely by saying that this formula over here, this holds for material line elements. That means delta capital X has to be a material line. It has to be a line engraved in the body. And as the body deforms, that line is also deforming. So it's a material line element. Whereas normal to a surface, it's not a material line element. Normal to a surface is not a material line element. So as the surface deforms, think of, for example, this stack of surface. Okay, so here is the stack of surface. And suppose it undergoes what is called shear. So I think I'm making a very bad picture. But you see, it has undergone shearing. Now think of the normal here. And here also the normal is still the same. But a line element along the normal, that has changed. It has become like this, the line element. Whereas normal is still like this only. So this is, so normals are same here. So what I mean to say is a normal vector is not a material line element. If it were a material line element, then it would have also changed its direction. You see, just like this is changing. So basically, we can't apply it because normals to surfaces are not material line elements. Okay? Any query? Are you? I hope you are following this.
Yes, sir. But sir, why this is relating like this? I mean, it is not clear to me.
Why it is?
The
Why
mm,
formula is like
yes, sir. So what does it means? So the
well,
the
you know
unit
the
the unit
formula,
vector cells are changing, or what it is representing?
well, as I said, this is representing the normal to the surface. And why is the formula like this? I mean, you have to tell the mathematics. See, you did the mathematics and it came out to be like this. So, I don't have any better answer than this. Why the formula is like this?
No, sir. What I mean is direction are same. Then what it is mean? Like it is not intuitive to think.
Which one? You mean in this picture here?
No, sir. The relationship small m and the capital M.
Yes,
Capital
direction
M.
are not, obviously, you know that when a surface deforms, the direction need not be the same. Then, therefore, small m and big M are not directed in the same direction. And you can see big M has to be transformed through F inverse transpose. F inverse transpose एक linear transformation है. You apply big M to it and divide by its magnitude, and then you get small m. Okay?
Yes, sir.
Okay, you can
So
think a
basically,
bit more about it. Yeah. Now, here comes your third question for assignment. Um, so the question that I'm giving you, I have not seen that question. So what, or I haven't worked it out. What happens to this red box in linear elasticity? Okay, that means when the displacement gradients are small. So you have to work it out. Okay. So this is problem 3, assignment 1. I mean, you have been enjoying till now, right? There was no assignments, you are just doing the class, but now you have to work a bit. I have lured all of you into taking this course, thinking that, you might be thinking it will be easy, but now I'm going to make your life tough. Okay? So I was just joking, by the way.
So for all the three counterparts of the assignment, what we have to do is we have to find out the linear elasticity, subsequent linear elasticity form of the
Result. Yes.
results that we have derived, right?
Yes, exactly. So those three formulas were general,
Yes, sir.
which holds for non-linear elasticity. But now you have to derive the linear elasticity result from those three formulas. You know,
Okay, sir.
if you recall your solid mechanics course, you must have derived the formula for longitudinal strain, for shear strain, for volumetric strain, but you derived it in a different way. And that way was not correct. You know, you can look back at your derivation, you will see that it has several approximations involved. But now you are going to derive those formulas very, very accurately. So you have the most general result. You apply this approximation that del ui over del xj is much, much less than 1 and derive all the formulas. Okay?
Yes, sir.
And in your assignment, if you can also show me how you had done it in your solid mechanics course, undergraduate, and what were the approximations involved there. If you can show me those things also, then I'll give you bonus marks.
Sir, in our undergraduate, as far as I remember, we just directly took down the formulas without venturing into derivations. So
Okay,
is
I
it?
think you must have done some derivation. If you haven't done, obviously, then you don't have anything to say.
Yes, sir.
Has anyone derived it? किसी ने भी derive किया था? I mean, किसी के teacher ने derive किया था इन formulas को? Shear strain का formula या longitudinal strain का formula through any physics also, any physical argument, let's say. They must have given some physical argument or volumetric strain formula. You know, for volumetric strain, for example, I remember my teacher, what did he say? So you have a cuboid, each of the sides are 1, 1, 1. After deformation, the sides become 1 plus del u1 by del x1, 1 plus del u2 by del x2, and 1 plus del u3 by del x3 because of the longitudinal strain. And then you compute the volume of the final cuboid, and it turns out to be, you know, the change or the strain turns out to be del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3. There the assumption was that even after deformation it remains a cuboid. We didn't take into account the change in angle there. So that's how we were told about the volumetric strain. For shear strain also we were said some physical argument. So I think many of you may not have been told this, but some of you may have been said. Then you can put it up in your assignment. Okay.
Okay, sir.
All right. Any more question? So I think I'm done for today. I have derived the various strain formulas, the transformation of normal to the surface. So this is all about the strain formulas. There is of course something more we'll talk in the next class.